Hi, my name is Dave Langer. Welcome to this first video in a series of tutorials on introductory data science using R. Um, I'd like to start this video with some information about myself. I don't plan on doing this with every video, but I figured I would just do it on the first one just in case it would be helpful for folks. So as I mentioned, my name is Dave Langer. I'm on LinkedIn in case you want to look me up for any particular reason. I work at Microsoft, and the only reason why I mention that is because if some folks look me up on LinkedIn and they found that out, they may be wondering why I didn't mention it. I'm mentioning it up front. I have no ulterior motive other than the fact I'm really into data science. Um, as you'll see down here, I have no technical religious affiliation. So even though I do work at Microsoft, I love all kinds of technology like R, Python, Java, as well as things like C Sharp, SQL Server, and Azure Machine Learning. So you won't get a lot of bias one way or another. I'm pretty interested in all technologies, and I try to use the right tech for the problem at hand wherever possible. In general, I've been working in IT for 17 years, with a 2-year stint in the product group is the only exception to that. Working in SQL Server in particular. If you've ever used the database projects in Visual Studio, I worked on that team for about a year or so, just to give you some background. I've spent most of my time in IT working in software development, business intelligence, and data warehousing. That's what really sparked my interest in data science about a year and a half ago. Because I see data science and machine learning and data mining in particular as just the next step in value over traditional business intelligence and data warehousing scenarios. You can think of BI and DW as really being this backward facing, looking back in time analysis kind of activity, whereas data science, quite frankly, is a lot about taking that information and then actually projecting forward in time, which is actually quite a bit more interesting, at least to me anyway. And I'm assuming to you as well. Otherwise, you wouldn't be watching this video. Lastly, I do want to apologize up front. I do consider myself quite the comedian, so I may sprinkle this video with a bunch of jokes, and quite frankly, your mileage may vary on how funny you find them. Okay, so let's move on to the goals of this series. First and foremost, I do want to make sure that folks who are watching this understand what the focus is going to be, so I'm not wasting their time. I am going to focus on quote unquote small data. And it's not because big data isn't cool. It absolutely is cool. It's just that I imagine my experience is like a lot of other people's experience, which is you don't really face big data problems in your daily lives in the business that you either support or the business that you operate. For example, I work at Microsoft. So as you might imagine, we have lots of places where there are big data. Azure, Xbox, Bing, and so on. But where I work in the supply chain organization in particular, we don't really have any big data problems. However, that doesn't mean that you don't get lots of business value from doing data science on small data. In fact, I would think that if you look at the Fortune 1000 overall, you're probably likely to get a disproportionate amount of business value from small data, especially compared to the amount of effort you have to put in to get the value out. Big data problems tend to be more difficult, quite frankly, so small data may be a bigger bang for your buck. Okay, another goal of this series is R. In particular, using R for data analysis and predictive modeling. As I mentioned before, one of the things that gets me really excited about data science is this ability to move from looking backwards and understanding what happened to using data to maybe predict or shape what will happen. And I think that's pretty cool. So I use R quite a bit, and I also use Python as well, but I tend to be more comfortable with R at this point in the game. And I also like its ability for making visualizations. I'm sure you can do the same thing in Python, but I'm more familiar with R, which is why I chose it for these series of tutorials. Lastly, if you're not already, I want to get you hooked on data science. While I didn't write this explicitly down in this Word doc here, I really hope that these tutorials will help folks in ways that I wished I could have been helped when I first started teaching myself data science and predictive modeling and data analysis about a year and a half ago. So I had a lot of struggles, but it's great. And I love being being involved in data science problems. So hopefully you'll get hooked on it as well. And I may hit other things later on in this series. I've been thinking maybe doing some text analysis videos with Python or something like that. But for right now, we're just going to stick with R and some predictive modeling. Okay, so let's go ahead and get started. Okay, so I am going to assume that you're reasonably competent technically. And I'm not actually going to go through the details of getting all this set up, but I'll give a little bit of an overview, right? So what we'll be using in these videos is RStudio. So you can get RStudio pretty easily. It's free. Just go to rstudio.com and you can go ahead and download it. So we get the powerful IDE, and we want the desktop, and we download the RStudio desktop, and here you go. It's multi-platform. Pick your poison. I'm using Mac right now. You may be wondering why. I do love Microsoft and Microsoft products. It just happens that I have a really cool video software package on my MacBook, and it's the only reason why I'm using my Mac right now. Everything we do is equally applicable on Windows or Linux, as you can see here. So pick your poison. You'll also need to download R and install that as well. R is the base language on top of which RStudio sits, and you can see that here. It's relatively easy. So I'm going to go ahead and pause the video here for a second, and that's nothing more than the ability to give you a chance to pause your own video in YouTube and then go ahead and download R and get it set up before we move on. Okay, I'm going to make the assumption that you've got R and RStudio set up and working. So the next thing that we're going to do is we're going to head over to the Kaggle website. And the reason we're going to do this is because I love Kaggle myself. It's one of the things that I've been using to help propel my skills in the data science arena. And it also provides a very good opportunity for some interesting data sets that allow us to explore some very cool things in this series of videos. So joining up on Kaggle is free. It's very simple. All you do is go to kaggle.com, click Start Competing up here, and then what we're going to do is go to the competitions. And Kaggle offers competitions where you can compete and earn prizes, and they also just offer some general knowledge-based activities, some competitions that you don't actually win anything for, but give you an opportunity to actually do some real data science work. And in particular, we're going to use the Titanic competition in this series of videos. And the reason for this is pretty simple. One is everyone should be relatively familiar, at least in the US and probably Western Europe as well, but probably all over the world, thanks to James Cameron, with Titanic, right? It was a tragedy that happened in the early 1900s. An ocean liner sank. You can see a picture of it here. A lot of folks perished. It was tragedy. So in data science, it's really important to understand the problem domain to give you context when you're looking at the data. So Titanic's a very simple problem. It's very well known, so it gives a lot of people context, which is one of the reasons why I selected it. You can click on the data here, and you can see the various files. What we're interested in here are the train files and the test files. Now, when you click to download each of these files on the links here, if you're not already a member of Kaggle, you'll be asked to create an account. So go ahead and do that and get the files downloaded, the train and test files downloaded to a location on your hard drive in preparation for the next part of the tutorial video. Now, there's other files here that you may want to take a look at later, but we're going to ignore them. If you're curious, they're essentially just other types of attempts at creating a machine learning data science solution that solves the problem. And, oh, I should probably mention what that is. So sorry about that. The point of the Titanic competition here is to take a look at the data that's provided by Kaggle and build a machine learning model that accurately predicts who will survive and who will perish. And what these other files are example attempts at doing exactly that, which is why you see model here at the end of the file names. So you can take a look at those if you on your own time if you'd like. That's no problem. However, we won't be doing a lot with that right now. Okay, so I'm going to go ahead once again pause to allow you a chance to download these files. So go ahead and pause now on YouTube, and I'll come back in just a bit and we'll move on to the next thing. Okay, cool, we're back. We're going to go ahead and keep this up on the background here in Chrome because this will be very interesting. This essentially is our data dictionary or our metadata, and it'll be extremely helpful for what we're going to be doing next. But without further ado, let's pop into R and let's start doing some fun stuff. Okay, so here's RStudio. Maybe some hardcore R people may think I'm kind of a weenie for using RStudio. I, however, love RStudio. It makes R much more usable, much more user-friendly. And that's actually a concern. R is not exactly the most friendly programming language in the world, but it is extremely powerful. So the first thing I'm going to do here now that I've got RStudio set up now is set my session. What this is going to do is it's going to tell R where I've stored all of my data files, so I don't have to use full paths to resolve every time I want to work with a file. So I'm going to go ahead and choose a directory here, and there we go. And you'll notice down here that essentially that series of menu clicks translated into some command line prompts here for the R engine, which essentially said set my working directory to my home directory here on my Mac, Kaggle folder, and then the Titanic subfolder. Okay, cool. Now, R is awesome for working with data. You can, once you get really good with R code, and I don't claim to be a master of R code, by the way, but when you get good with it, you can actually do a ton of stuff with very little amounts of code coming from your fingertips. So for example, reading in CSV files is dead simple in R. You can literally use what's known as the read CSV function. You provide it the file name. Now, of course, you could use the entire file path, but I set my working directory to prevent me from having to do that. And I know that the CSV files have headers, so I just say the headers equal to true. And I can run this code by simply highlighting these two lines and clicking run up here. And you'll see down here that it gets executed in the R console automatically for me. And the RStudio depicts my environment of what variables I have loaded in memory. So what I have here is a variable called test and a variable called train. Now if I click on these, I'll get a visual exploration pane of the data here. And you'll notice that it's very spreadsheet-like. It's essentially just a table of data, or a matrix if you're mathematically inclined. And you can just take a look at the data here. Now, behind the scenes, if we hover over the variable here in the RStudio UI, you'll notice that it says, hey, test is a data.frame. Now, data frame is a particular data type inside of R, which is specifically designed for handling tabular data. Now, as you might imagine, those of you who've worked with databases or maybe you've worked with spreadsheets a lot of the world's data is tabular in format, and R works very well with tabular data. And you can see here we've got, 418 observations of 10 variables in our test set. And you can see the names here and some data values. We can also take a look at the train set. Now this is important because you'll notice the first thing here is that in test, the first column I have of variable values here is P class. But if I look at the train set, I don't have that. I have survived. And this is pretty important. In machine learning terms, what we're trying to do here is build a classification model. Literally, we're trying to tell the computer to build an asset from this data that enables it to either say with a certain amount of certainty, does someone not survive? Do they perish? Or do they survive the sinking of the Titanic? And what differentiates our trained data from our test data is the fact that we have these values that said, yep, Mr. Owen Harris Brond did not survive, but Mrs. John Bradley Cummings did survive. And here are all the data points that are associated with her. And what that allows the computer to do is to use a machine learning algorithm or algorithms to use this data and learn from the data the patterns between who survived and who did not in the data set. And this is a pretty key point. You use machine learning or data science techniques when the pattern in the data, the signal that you're trying to understand, is either too complicated or it would take too long for human beings to divine it, to examine the data by hand, understand the patterns, create algorithms or logic to actually implement the patterns and also do the classification. So that's what machine learning is really about, and we'll see that more as we go through the data analysis. Okay, great. So we've got our data loaded. We've in our test and train sets. Cool. Now what I want to do though is that for my overall data analysis, I want to actually combine these two data sets into one big superset of data. So what I'm going to do here is you write a little R code. Well, I've already written it because I'm sure you don't want to see me type it. We're going to go through a little R code here to actually start to combine it. Now the first thing that you'll notice over here is that the train set has 11 variables because it has the survived label, and the test set does not, right? Because we're going to train our machine learning model with this label, which is the 11th variable, and then we'll then have this test set to actually be able to decide whether or not the model that we built is any good. But to combine these two into one set, I need to add a variable to the test set. So this is what I'm going to do with this line of code. And we'll take a look at it piece by piece. So the first thing that I'm going to do is I'm going to use the data frame function. Now the data frame function, it allows you to create new data frames, oddly enough, or intuitively enough, depending on how you look at it. And one of the cool things about R is that it has a pretty rich help system. So for example, if you ever wanted to know more about the data frame function, you can go down here to the console, type $data.frame, hit the enter key, and what you'll get over here is some help on the data frame function from the R help system. And it's pretty rich, and this is indispensable, to be quite frankly, as you're ramping into doing data science with R. The R help system is your friend, and it covers a wide variety of topics, from functions to data types to syntax. It's just immensely helpful. So we're using the data frame function to create a data frame. And in particular, what we're doing is we're saying, okay, hey, I want to add a variable to this data frame that I'm creating called survived, which would make sense because as we saw, there's a survived variable in the trained data set before, and we'll need to add one to the test set to make it 11 variables and make it on par with the trained set. Now what I'm doing here is I'm using another function from R, and let's go ahead and take a look at that in the help system. The rep function, which allows you to replicate elements. Essentially, it's a way to repeat values. And so what I'm doing is I'm saying, hey, R, repeat the value of none, and the number of times to do that, I want you to repeat it, is equal to the number of rows, that's what nrow stands for, in test. And again, let's go ahead and ask the help system. The nrow function returns the number of rows / columns in an array. So what I'm saying is, hey, the number of rows in the test set, which should come back 418, repeat the value of none 418 times and assign that to the survived variable. And then I want you to combine that variable with the test variable. And this syntax deserves some explanation. Data frames can be indexed using this kind of syntax between square brackets. This essentially tells you, hey, I want to subset the test data set, or the test data frame, excuse me, via rows and columns. So for example, if I was interested in the first row and the fourth column, I would do this syntactically in R, and I can run this code by highlighting it, and again, hitting the run button, or hitting Alt Enter or Command Enter, depending on what operating system you're using. And what you'll see here is a value gets spit back, and that is the cell that would be in the view of this data set on the first row and the fourth column. So I'll check that. So first row, 1, 2, 3, yep, fourth column, and there's the value. Now what this syntax tells me is, I want to access one thing. If I leave this blank, what I'm telling R is I want you to use all the rows and all the columns. So basically what this code is saying here is take the entire table or the entire matrix or the entire data frame of test, all 418 rows of 10 columns, or in R speak, 418 observations of 10 variables, and combine it with a list of 418 strings of none. And then return that all back as a big data frame and then assign it back to this new variable called test.survived. For those of you who are programmers at heart, you may be wondering what this is. This is the equivalent of the equal sign. It's kind of an R oddity that says, hey, assign the results of this code statement to this thing here, and it's basically a new variable. So we'll go ahead and run this line of code. And sure enough, you can see, hey, we've now got a test survived variable, it's new, of 418 observations of 11 variables. Let's go ahead and take a look at that. And sure enough, none, all up and down. Sweet. Now that we have our dimensions the same between this modified version of the test data set, or the test data frame, and the train frame, they both have 11 variables, I can now combine them using the rbind function, which stands for row bind. Again, let's go ahead and hit the help system. And you can see there's also another function called cbind, which stands for columns, intuitively enough, versus rbind. And what this is doing is telling R, hey, look, take the train data frame, the 891 observations of 11 variables, as a table, and then append to it, row by row, the test.survived variable, which is 418 observations of 11 variables. Now what that should give us in the end is a combined data frame, a table that has, 1,309 observations of 11 variables. So let's go ahead and run that line of code. And sure enough, that's exactly what we get. And we can take a look at that, and we can see, oh yeah, this is the zeros and ones, it's the labels, and if we scroll down far enough, then we get into the nones, right? We've just appended, after 891 records. Okay, no, I do not want that. Thank you. 892 on down is the test records. Great. So now we have both of the records combined into a single data set. Okay, cool. So that's a pretty long explanation for only 4 lines of code that allows you to do some things that are pretty integral to doing data analysis on data sets that would take a lot more lines of code in something like Java, for example. Now that we've got our combined data set, we should probably talk a little bit about data types in R. So what I'm going to do is take a look at the str function here, and once again, let's pull it up in the help system. And the str function essentially allows you to ascertain the structure of an arbitrary R object. Essentially, what is its data type? Describe to me what this data type, this instance of this data type is. So we'll go ahead and run the str function on our combined data set and see what R tells us it's built out of. Okay. Now you can see here that, what R tells you is that the data.combined variable is a data frame. It's 309 observations of 11 variables. We already knew that, but it's good to confirm. And it's composed of these particular variables and variable types. So the survived variable is a character. And you can see it's 0, 1, 1, 1, 1, 1. And that would make sense because we know that around 892, in around row 892, we go from collections of zeros and ones to the word none, because we put that up here, and then we did rbind and combined them together. So it makes sense that survived would be a character string. Now we know the p-class variable now is a integer, and you can see the various values there. And then we look at name, and we see this thing called a factor. And if you're not familiar with R, that may be a little bit confusing. So, hey, no problem. Let's ask the help system about factor. R is case sensitive, so apparently it didn't like capital F. Didn't know that, but it did like lowercase f. And you can see here the help system gives you some help on what factors are. And a factor is used to encode a vector as a factor. And this is what's really key, is right here in terms of understanding factors. Factors are what R denotes categorical or enumerated type variables. If you're an old school programmer who maybe used C or C++ or any of the derivatives of C like Java or C#, enums, same idea, right? Which is this idea that you can define a variable or a data type that only takes on a limited set of discrete values. And another way to think about it is factors are akin to drop-downs in a web UI. For example, if you've ever been on an e-commerce site and you had to pick your state, province, or your country of residence, usually you get a drop-down. It has a finite number of values. In the United States, primarily you'll see 50 values for the 50 states of the Union. And that's an example. So factors are a way of encoding numeric or character data into a discrete data type that then can be used as part of your data science and machine learning activities. Because as you might imagine, computers don't like strings in general, and machine learning algorithms like them even less. So factors are a way of translating these things into a representation that works well. You'll also see that the sex variable here is a factor with 2 levels, female and male, which would make sense. There's an age variable, and it's considered a numeric. And you can see the numeric, blah, 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 and then NA. Now, you may be wondering what NA means. If this is a numeric, why is there a string value in there? And the answer is that the NA denotes in R the absence of value. If you're familiar with programming or databases, NA is equivalent to null, the absence of value. So every other value in this list you'll see is numeric, but this one was missing. So NA denotes the fact that there is nothing there. You can see there's the SIBSP and the parch variables. They're both integers, factors, so on and so forth. Okay, so by default, this is how R interpreted the data that we read from the CSV files that we downloaded from Kaggle. Now, that's not particularly useful right now. We're going to have to actually change this around a little bit, but I did want to introduce the variables a bit, variable types a bit, so that you can understand why we're doing the things that we're going to be doing later on in this series of videos. Okay, so let's go back to Google real quick, or excuse me, not Google, Chrome, and let's take a look at these data types here in terms of their definitions. Now, p-class is currently in R as an integer, but you can see here that in actuality, p-class is representative of essentially the class of ticket that the passenger bought, whether they were a first-class passenger, a second-class passenger, or a third-class passenger. In fact, you can see down here in the special notes that p-class is actually a proxy for socioeconomic status, which is a very politically correct way of saying, essentially, were you richer or were you poor? Okay, cool. This probably shouldn't be an integer value. It's not a number. We're not actually going to do any multiplication or division on these values for the p-class variable. It really is a factor. It's you're either first class or your second class or your third class, and that's essentially all we need to know. So we can go ahead and tell R that we want to change the p-class variable using this line of code here. And what we say is, hey, look, take the p-class portion of the data.combined, and you use a $sign in R to actually address the p-class portion of the data.combined data frame and turn it into a factor. Okay, so we'll go ahead and do that. And let's go ahead and run this line of code again, and then we can see that, in fact, indeed, p-class used to be an int, and now p-class is a factor. Okay, that's good. And we can also take a look at survived. Now, we know that survived shouldn't be a character string because, as I mentioned before, machine learning algorithms don't like character strings. So we should probably turn that into a factor as well. And what we would expect is that we would get three values, of survived once we convert it to a factor. And let's go ahead and take a look at that again. Yep. And there you go. Survive is a factor with three levels, 0, 1, and none, which is good. Cool. So we've kind of massaged our data a little bit here into a format that's more amenable to both machine learning as well as data analysis by making the things that should be categorical variables or factor variables that way, as opposed to what R originally had loaded them in as. Okay. Next up, let's take a look at survival rates in aggregate. As I talked about before, the whole point of this Titanic competition is to build a machine learning model that can predict whether a passenger survives or does not survive the sinking of the Titanic just based on the data that's provided. So one of the first things we want to know is, okay, what's the distribution look like of those people who lived and those people who did not? And what you can use here is the table function. And again, when in doubt, use the help system from R. And there you go. There's the help file for a table. It basically takes some data and puts it into a tabular format for you. And you can see the results here. We said, hey, Mr. R, grab the survived variable and tabulate it for me and then spit it out as a table. And essentially what it did is exactly that. So out of our 1,309 records, 549 people perished in the Titanic, 342 survived, and then 418 is none, which is what we would expect because this is our test set, not our training set. So the first thing to note is that, as you would expect if you know anything about the history of the Titanic, is that the data is a little bit skewed. More people did not survive than did survive. In fact, pretty close to twice as many people perished as survived overall. And that's going to be important because machine learning algorithms often will often fit the data that they're provided. So for example, here it's a good bet that in general, if you didn't know anything better and you had to place a bet on whether someone survived or not, you would say, no, they're probably going to perish just because statistically they're more likely to not survive. And machine learning algorithms essentially work the same way. The more skewed the data is to one side or the other, the more likely, without some help, that the machine learning algorithm is going to just pick the most common scenario. In the most extreme example, if only one person survived and 549 people perished, statistically speaking, you would just always predict that you didn't survive because you would be right, 99.99 something % of the time. And that's what a machine learning algorithm will do. So we always want to be cognizant of skew in the data, especially in the labels, because sometimes we have to do some pretty interesting things and sometimes difficult things with the data if it's heavily skewed. This data is not too bad. It's less than 2 to 1. That's not too bad. If it was like 10 to 1, then you would have to start looking at some interesting techniques to combat that. But this is interesting. But it is in line with our expectations, which is, as we know historically, more people perished on the Titanic than survived. All right. So next up, let's take a look at the distribution across the classes. As we know from our metadata dictionary that there were 3 classes of passengers. And there was first class, second class, and third class. Now, generally speaking, as you would intuitively expect that there would be far more people probably in the lower classes than in the upper classes. So let's see if that's actually true. Okay, so I executed this line of code. Once again, it's just, hey, execute the table function on the P class variable. And what you get out is the distribution across the classes. And this is particularly interesting and not both at the same time. Now, for example, there's a lot more people in third class than there are in the upper classes, and that would make sense, right? Just like if you've ever flown on a commercial airliner, you know that the vast majority of people are not in business or first class. They are in coach or economy or whatever the designation is for folks who didn't pay a lot for their ticket. So that makes a lot of sense. Now, what is interesting, though, is that you would expect that general rule of thumb to apply for the upper classes as well. For example, you would expect that there would be more people in second class than there would be in first, but in fact, that is not the case. So that could be potentially interesting from analysis perspective, for creating a machine learning algorithm. There are some rules to understand who, or some patterns to understand who perished and who would not, just based on data. So this is interesting. We should keep this in the back of our mind. So you could get some pretty interesting information straight out of R just by using the table command. But human beings tend to find, visualizations a much more productive means of actually understanding and gaining insight from data rather than just looking at tabular representations. So what we're going to do is next take a look at some graphs, some plots of this data to see if we can derive some more insight from it. And in particular, we're going to use ggplot2. ggplot2 is essentially the de facto standard in the R community for creating high quality visualizations of data. Now, getting ggplot2 is extremely simple. You don't get it in base R by default, but it's very easy to add. So all you need to do is go to the Packages tab over here on the right side of the RStudio UI and just click Install. And just type in literally ggplot2. And click Install. And what you'll see down here is the command line will actually execute an install package. And obviously you have to have internet connectivity, but it'll download and install ggplot2. And then using the library command, you can then load that package, that library, up into memory and then access the functions of ggplot2. So we just go ahead and run it. And interesting enough, it says, hey, look, you got an error. I can't load ggplot2 because I need a package called stringer. All right, no problem. Let's go ahead and load the stringr package. Great. And let's go ahead and try and rerun this line of code here. Excellent. So now we have ggplot2 loaded successfully, and we can use its functions. Now, we've got a hypothesis here that I want to explore, which is, we know that there was 300 and something folks. Let's go ahead and scroll up here so you can see this again. 323 folks that were in first class. So I've traveled on an ocean liner before, maybe other folks, maybe you have as well. And typically what happens is that the more you pay for your room, the higher up on the ship you are, and which also tends to make you closer to the lifeboats. So it'd be interesting to see, hey, did rich folks, that is people who were in higher classes, have a different survival rate than those that were in the third class, those people who were lower in the boat? So we can go ahead and test that. Since we can only tell if you survived or not in the training set, we're going to go ahead and turn P class on the train set, because if we do a quick str on train, you can see here that the P class variable is not a factor like we did with the combined data set. So we'll go ahead and fix that real quick here by running this line of code. And then we're going to go ahead and call ggplot. Now this is a bit confusing because the function is ggplot out of the library ggplot2. And in case you're curious as to the reason why, there was a first version of ggplot which essentially got replaced by ggplot2, but the name of the function stayed the same. So you use the ggplot function out of the ggplot2 library. And let's take a look at some of the syntax here. So ggplot is the function, and of course you can pull that up in the help system, and you can say here, create a new ggplot. Okay, well, not particularly helpful. But what is helpful is that if you scroll down, it gives you a whole bunch of examples of how you use it. But you don't need to worry about that because I'll explain. So the first thing that we passed into the ggplot function is the data that we're interested in plotting. Now, more often than not, that's going to be a data frame, which is what we have here, right? We have the train variable, which, as we know from over here in the upper right corner, is a data frame. Great. Next, we have to tell ggplot2 some aspects of the aesthetic. That's what AES stands for. And again, we can go ahead and look that up in the help system. Generate aesthetic mappings. And what that essentially means is you're controlling the way that the graph or the plot is going to look. And what we're saying is, hey, the aesthetic will have an x-axis corresponding to the p-class variable of the train data frame. And we're also telling ggplot that we would also like a fill color to be used. This is optional. You have to specify an x at a minimum, right? You have to have an x-axis at a minimum, otherwise you're not going to have a plot. But the fill variable is optional, but it's going to be helpful because what we're going to say is, look, color code the resulting plot based on the survived variable. Now, as you see down here, survived actually isn't a factor because we haven't converted it yet like we did with the combined frame before. So I'm just illustrating to you here another option that says, look, I can convert the survived variable, which is currently an int, into a factor on the fly by using the factor function. And again, whoops, pull it up. Oh boy. There we go. Pull it up in the help system. There's factors, right? We saw that before. So this is a function that I'll convert it on the fly to a factor. And then lastly, we're now telling ggplot, look, and you've got the data, you've got some aesthetics that I'm providing you, what the x-axis is and what the fill colors should be based on this variable survived. What I want you to actually plot out is a histogram of a width of about a half. And go ahead and display that to the screen. And then these last bits just say, look, I want to add an X label called P class and a Y label called total count. And this is saying, hey, I want to assign to the fill a label of survived. And let me just run this and it'll become much more clear in a second. Okay, and here you'll see here in RStudio the plot. And you can see here the X label is P class, the Y label is total count, and the fill over here is labeled survive. Now, what you'll notice is that this part here generated the green and, I don't know, reddish, orangish color here. This says, look, give me a histogram for each value of P class, but then break it down, bisect it based on the survived variable. So then that'll give me a visual indication by p-class the total count of people who survived and the people who didn't survive. And what you can see here from this plot is that our hypothesis seems to be confirmed, which is, in general, if you were in third class, unfortunately, you were far more likely to perish, all things being equal, than you were to survive. Whereas if you were in first class, you seem to have a much better chance of survival than perishing. And that kind of makes sense. And then interestingly, we can see in, second class, it looks to be pretty close to 50-50. So that's pretty powerful, right? Because that's telling you a lot, right? It's saying, look, from a data analysis perspective, it seems that p-class is kind of important for our problem at hand, which is determining the pattern of who survived and who didn't on the Titanic. Okay. Now if we go back real quick here to Chrome, we've kind of taken a look at these two variables initially. We've said, hey, let's take a look at the initial survival rates. What's the distribution? How does that work? Let's take a look at the p-class variable. What's the distribution? And then we've also combined those two in this pretty intuitive plot, which is actually arguably more powerful, more informative than just looking at these previous table presentations that we saw earlier, right? These right here. I mean, this is interesting, but when you combine the two visually, it really does pop. Yeah. So there's a lot more people in third class, and they were far more likely to perish than there were people in first class. Interestingly enough, there were far more people, or there were more people, I should say, in first class than in second class. And as you move down, your odds of survival decrease pretty dramatically by the time you hit third class. Now, if we go back here to the metadata for our data set, the next thing that we need to take a look at is the name variable, right? Because data analysis at base isn't, it's a pretty methodical process here. So we're going to go ahead and take a look at the head command. And there's a couple things that we need to look at first before we talk about the head command. So there's this as.character thing, and to understand why I put that in there, or why we need it, let's go ahead and look at the structure of the train data frame again. And if we go down to name, you can see that it's been labeled a factor variable, which is pretty interesting. Essentially what it did was it says, look, hey, it's a factor with 891 levels, which essentially means every row had a unique name, and it created a categorical variable with 891 levels. Another way to think about it is, in a dropdown in either a Windows app or a web app, you would have 891 entries, a very long list of entries, in the dropdown. And that doesn't work for us. So what this does is this says, hey, R, I don't really want you to think of this as a factor. On the fly, just give me back the strings. So essentially give me back the names. And then issue the head command on that. Now if we look at the help system here, the head command just allows you to take a look at the first or last part of an object. So essentially what it's going to do is it's going to say, hey, look, grab all of the names, turn them into character strings, and just give me the first few off the top. So we run that. Lo and behold, we can see first name, second name in the list, third, and so on. And this is particularly useful. The head command is extremely useful to just give you a general sense of the data. And what we're seeing here in the data is, first and foremost, that the data is kind of formatted in a very formal way. What you have here is, it appears to be the last name with a comma, then a title, first name, middle name. And you can also see here, last name, title, and then I'm assuming here that this is, in fact, this lady's husband's name. And then back here, you actually get, I'm assuming, although it doesn't necessarily tell me, but let's double check that to be sure, that that is her maiden name, the name she had before she was married. And let's see here if there's anything in. No, does not. However, we could probably infer that pretty easily. So for the time being, let's just assume that that's in fact the case, that this is a married woman, this is her husband's name, and this was her maiden name before she got married. And we can see here there's a Mr. and a Mrs. and a Miss and a Mr., which is kind of interesting. So the names are formatted kind of interesting. That may be germane later on, so it's worthy to note. Okay, moving on. So let's just take a look and see how many unique names are there across both the train and test sets. As we saw before, with the train set, every name was unique because we got 891 levels and there was exactly 891 observations in the train data frame. Okay, so let's see across the combined data set, which we'll take the name from the combined data set, then make it a character string, and then we'll use the unique function. So let's go ahead and pull that up. Okay, so it's exactly what you expect, right? Unique function extracts unique elements from a vector, data frame, or array, but with the duplicate elements removed. It's exactly what we want. So, and then lastly, we say, okay, give me the length function on top of that, and length of an object. I mean, it's almost silly for me to type this into the help system because you could probably infer what it means. But let's just go through it all at once. Grab the name from the data.combine data frame, which should be 1309 values. Convert them to a character string. Find out which ones are unique, and then tell me how many are actually unique. And if we run that line of code, we get 1,307 unique names. That's interesting because we would expect that we would get 1,309, which means we've got some duplicate names, probably 2 duplicates. So let's go ahead and take a closer look at that. Now, this line of code gets even more complicated, but let's go ahead and break it apart just so we understand what's going on. So we'll go from the inside out. So now I've got some duplicate names. I need to determine whether or not that's because of it's legitimate. For example, John Smith is a common name. Maybe there's more than one John Smith. Or do I have some bad data in the data set, which I would need to know, because if I've got duplicate records, I would need to either take the duplicate records out or deal with them in some other way. But it's nice to know what my situation is. So how we do that in code is we say, okay, go ahead and grab the combined names, the names from the combined data set, convert those to a character string, and then invoke the duplicated function on that. And let's take a look at duplicated in the help system. Okay, so determine duplicated elements. Okay, great. So what this is going to do is it's going to go through all of that, and it says determines which elements of a vector or data frame are duplicates of elements with smaller subscripts, and returns a logical vector indicating which elements are duplicates. Okay, great, or rows. So that's going to say, look, I'm taking a look at 1,309 character strings, and I'm going to return you back which rows of those 1,309 are the actual duplicate rows. Sweet. And now we've got which. So what's which? So this says, okay, it's very much like, if you're familiar with SQL, it's very much like a where clause. Essentially, it's a way of actually honing in on the data that you're interested in. So what we say here, popping out a level, this gives it some context, is great. From the data.combine data frame, I want to grab the name column, but I only want to grab those records which are duplicated. Great, that should pull out essentially four, we're thinking 4 records. Maybe it's it's definitely 4 records, but maybe it could be 2 names duplicated twice, or it could be 1 name duplicated or triplicate, repeated 3 times. We'll have to see, but this should be pretty intuitive. This essentially is like a where clause in a SQL query. And then take that, turn it into a character, and then stick it in the dupe names. So we can go ahead and run that. And if we go over here, we can see, in fact, okay, dupe.names is a character string consisting of 2 values, Mr. James Kelly and Miss Kate Connolly. Excellent. So what we see is we've got 2 names that are duplicated twice for a total of 4 times, which would then explain the difference that we saw earlier of 1307 versus 1309. Okay. So let's go ahead and take a look at, now that we understand which names are duplicated, Mr. James Kelly and Miss Kate Connolly, we need to actually go through the entire combined data set, and we want to pull out all of the records, all of the observations that matches those names, and then display them. So then we can take a look at it and say, hey, are these people different people, or are they the same people just duplicated in the data set? And then we'll address that if we need to. So how we do that is we say, okay, great. Go through all of the names in data.combine, and if they happen to be in, if the current name, as I'm iterating through data.combined, all the names, if the current name I'm looking at in that iteration is in the set of names as exemplified by dupe.names, which we know from over here are Mr. James Kelly and Miss Kate Connolly, go ahead and pull that record out. Again, remember, this is the which. So if you're familiar with SQL, hey, grab from data.combine those observations, those rows where the name is in the duplicate names, and then return me back all of the data, right? Because remember from our previous example, if I only wanted one thing, I'd put a number in there, but since I have no numbers, R says, oh, you want everything that comes back. So now if we run that code, we pull back 4 records, which is kind of what we expected, and we can take a look at them. Then we can say, okay, here's Miss Kate Connolly. She survived. She's in 3rd class, female. She's age 22. She has 0 for these values. Here's her ticket number, how much she paid for her fare. She had no cabin assigned apparently, and she embarked on Q, which we'll see later is Queensland, but that's not really germane for right now. Now we can go down to this Miss Kate Connolly. She has none for survive, so she's obviously in the test set. She's also in 3rd class, which is kind of suspicious. She has the same name, but she has a different age, she has a different ticket, and she has a different fare. So it's probably safe to assume that, in fact, these are just 2 women who had exactly the same name. And the same thing for Mr. James Kelly, which makes sense. Kate Connolly and James Kelly, those are probably fairly common names in either the US or the United Kingdom, and it wouldn't be unheard of for there to be some, maybe those folks to be 2 folks with the same name of those names on the ship at the same time. So looks like we're pretty good there. So okay, so we can, at least from a name perspective, we could say, okay, great. Doesn't look like we have any duplicates. All the names are unique. Everything checks out, and that's good. And that's something that's extremely important when you're doing data analysis, especially in the context of trying to build a predictive model, is you need to go through the data with a fine-tooth comb to try and find any anomalies that you can. So this is an example here of where we may have had an anomaly, but in fact we don't. We validated that in fact these are different people, so the records don't need to be modified in any way or removed. Okay, now one thing that's kind of interesting, as we noted before, moving on, is within the names there are these titles. And they seem to be pretty important because as we saw up here, we got Mr., we got Mrs., we got Miss. Every record seems to have one. So they took a lot of great pains to put them in there. So what that should tip you off as a data sleuth is maybe there's something interesting going on there. Maybe there's a pattern. Maybe there's some predictive power with these titles. So that's probably worthy of some further investigation. So what we'll do here is we'll load up another library. We saw this earlier when we tried to load up ggplot2 and it said it wanted the stringer library. We'll go ahead and load it. It's probably already loaded, but it never hurts just to explicitly load it again, just to make sure it's okay. And we're going to go ahead and take a look at saying, look, what's up with this Miss and Mr. thing, right? These titles, can we derive anything from them? In particular, is there any correlation between these titles within the names and any other variables? For example, the SIBSP variable. So the first thing we're going to do is we're going to take a look at the string detect function here. Again, let's pull it up in the help system. And we can see here it detects the presence or absence of a pattern in a string. And what we're doing is we're saying, look, grab every single name in the combined data set and detect to see if miss, period, is in that string. And if so, again, here's our which essentially is like a where clause in SQL. And it's saying, look, grab me every record out of the combined data set where miss is in the name and give me back all of the data. Remember again, because we've got a blank here, nothing. And then store the result of that in the misses variable. And I just want to take a look at the first 5. Now this is worthy of note. We haven't seen this syntax yet. This is the way of denoting a range in R to say, look, I want a range of 1 to 5 of the rows of the observations here. And similarly, I could do something like this as well. And what this would say is, hey, give me the first 5 rows, 1 through 5. Oh, that's also worthy to note. For those who are programmers, R indexes from 1, not from 0. So give me the first 5 values. And then also give me the first 5 columns. Well, we don't want that. We want all of the columns, so we'll just delete that and run these 2 lines of code. So you can highlight them both, and just click run. And there you go. You can see the first 5 rows here. Now they all contain the word miss in the name, the term miss in the name, which is excellent. And then we can see all of the rest of the variables associated with it, and we can just look at it and say, hey, is there anything interesting going on here? Well, the first thing you notice is that out of the 5 records, 4 of them survived. So that's 80%. That's probably significant given what we saw earlier when we took a look at the tabular count of survived versus perished, and that's pretty good. What's even more interesting is that not only did most of the folks of the first 5, did 4 out of the 5 misses that came back, survive, but 4 out of the 5 misses were also in 3rd class, which is even better yet, because as we saw, your survivability rates decline dramatically in 3rd class versus 1st class. So this is already getting to be pretty interesting from a data analysis perspective. Now moving on, the names, okay, great. They're all female, which would make sense. And you look at the age. Now the age is interesting because there's quite a variance here. The range is all the way from 4 to 58, which is highly interesting. Now if you move over here, you can look at this first column here. I'll call it the CIBSPA for lack of a better way of describing it. So let's take a look at the metadata for CIBSPA and see what Kaggle has to say. So CIBSPA denotes the number of siblings or spouses on board. Okay, interesting. Now we'll notice that the only one of the 5 here that have any value here is 4 years old. So I think it's probably a safe assumption to say that a 4-year-old girl is not married. So that probably indicates that she is traveling with one sibling and not one spouse. And you notice the rest of these are 0. And then also we have the parch here. So if we go back to parch, you could probably guess what that means, and that's the number of parents or children on board. And again, with a 4-year-old girl, it's unlikely that she has children, beyond probably biologically impossible. So I think it's safe to infer that this is a 4-year-old girl who is traveling with one sibling and one parent. And that's significant because, again, you'll see here all zeros. So what this seems to infer when you combine it with the ages here is that Miss denotes a non-married woman, generally speaking, which is potentially interesting. There may be some predictive power there. Also, you can tell, at least from this very small data set, that not only is it an unmarried female, they may tend to be younger in age in general, which would make sense because in the early 1900s, it was pretty common for women to be married past a certain age, so that would make a lot of sense. So that's interesting. So given that we just came up with a hypothesis that there may be some correlation between titles and age, let's go ahead and take a look at Mrs. now. So we'll do the same thing, right? We'll just do the same exact code except for with a string of Mrs. instead of Miss, and see what we get. Well, that's wrong. Apologies, typo there. Okay. As again I mentioned before, right? R was case sensitive and I had a capital N there, so once I changed it to a lowercase n, it worked just fine. Okay, so with Mrs., as you would expect, we've got a number of patterns going on. All of these women survived. In general, they tended to be in the upper classes here of passengers. They all seem to have the same general pattern, which is their husband's name first, and then what appears to be their maiden name, we're assuming, in parentheses behind. And well, so this will in the modern day, this would raise a bit of an eyebrow, but in general, you can say that yep, it seems to be Mrs. indicates in general older females, as you can see here, and it looks like most of them tend to travel with a spouse. Maybe that's a sibling, but maybe for the time being, we'll infer they're mainly traveling with a spouse. And there you have it. This is also immensely interesting. I mean, we just sampled the first 5, and they all had to survive, which, as we know from our previous distributions, is pretty interesting. Let's also take a look at men. So we're going to take a little bit different tack. Rather than going off of the actual title, let's just grab the first 5 male records out of the combined data set and just take a look at their names as a result of that and see what happens. Okay. Oh, well, first thing you'll notice is that it sucks to be a guy on the Titanic, apparently. And so all these men perished. Most of them were in 3rd class, with the exception of this gentleman here in 1st class. Ages are all adult males. There's a missing value here, so we don't know about James Moran. But this record's interesting. Age 2, and it's not a Mr., but it is a Master. So like Miss, maybe this is indicative of, if you have a title of Master, that's indicative of a male child, a boy, as opposed to an adult male. a man. And this would also be borne out here because a 2-year-old is unlikely to be married to 3 women simultaneously, so that's more likely that this Mr. Master Gosta Leonard Poulsen is traveling with 3 of his siblings and 1 parent. And that was probably borne out by the fare because he's in 3rd class. 21 pounds for a 3rd class ticket's pretty expensive, so that would be probably indicative of a family traveling together. Okay, so that's particularly interesting. I think I'll wrap up this first video with one last look at names, in particular titles. So we've looked at some tabular data here, and we've inferred quite a bit of interesting things from the data already. It appears that title's pretty interesting. We've seen some general patterns around sex and class and survival rates, some proxying for potentially of these titles for general and ages, as well as the sibling, spouse, and parent-child variables. But let's go ahead and visualize the data because, as we've said before, tabular data is good, but visual data is usually even better yet. So I'm going to make a little room in my plots area here. I'm going to clear this guy out. So what I'm going to do is I'm going to expand upon the relationships between survived P-class by creating a new title variable, by literally extracting out of the strings the embedded title value for the name and adding it as a new variable at the end of the data frame. So we'll go from 11 observations, 1,309 observations of 11 variables, excuse me, to 1,309 observations of 12 variables, and the last one being title. And then that way we can actually plot out, visualize how title is related to both survival rates and P-class. That may be an interesting visualization. So the way I'm going to do that, it's all right. Actually, let's go ahead and just make this full screen to get a little more real estate here, is I'm going to create a little utility function. So this shows some of the syntax in R for defining a function. So I'm going to define a function that takes a single parameter, which is the name, and I'm going to name this function extract title. Makes sense? So the first thing I'm going to do is I'm going to convert the name as a character, because as we've seen previously, these are treated as factors by R currently, so we'll turn it from a factor into a character string. And then we'll use the grep function, and let's go ahead and pull that up. Those of you who are programmers or are familiar with Linux, Unix, then you already know what grep is. So grep is a pattern matching function. And what we're going to do is we're going to say, hey, if you recognize the pattern of miss within the name, great. And if the length of that is greater than 0, which essentially tells me, yep, you found it, it's within the name, just return miss as a string. Do the same for master, do the same for Mrs., do the same for Mr., and if you find something else for what other reason, just return back other. Great, that's a pretty simple function, right? Moving on, here's some code that actually takes advantage of the function. So we're going to create a variable called titles, and we don't have anything to stick in it right now, so we'll make it null. And then we're going to go ahead and loop over all of the values in data.combine. So we said, hey, grab me the number of rows, which we know to be 1,309, and go from 1 to 1,309. And each time, go ahead and call this function. So the I value will be our index. It'll go from 1 to 1,309. So grab the first row, the first observation from the data.combine data frame, grab the name, pass it into the function, and then we need to take a look at this real quick. The C function, this stands for concatenate, or combine, excuse me. So what this does is this essentially says, take whatever comes out of this function call and add it to titles. And basically what we're doing is we're just building up essentially a vector, an expanding array of these values that come out of the extract title function. So essentially it'll be like a collection of strings. It'll be like, maybe it's miss, 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 master, 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 Mr., Mr., Mrs., Mr., Master, Miss. You'll get a big long list, and eventually you'll get 1,309 of those because we are iterating through the entire combined data frame. And then at last point, we'll say, hey, look, once I'm done with that, create a new variable on data.combined. So make it a data frame of 1,309 observations with 12 variables, the 12th one being a new one called title. And go ahead and cram in all the titles that I created through going through this loop and calling the extract title function. But before you do that, on the fly, convert that to a factor, because as we said before, you can't do a lot of really cool analysis on raw strings. So we'll turn the miss, the master, the misses, the mister, and the other string values into a factor of 5 values. And then that allows us to do some interesting analysis on that. So just highlight all this code and run it. And we'll see over here that we now have 12 variables. And if we click on it and pull it up, sure enough, you can see a title column has been added to the end, and it's got all of our values. And just to double check, we can look at the first 3, Mr., Mrs., Mrs., check the names, Mr., Mrs., Miss, sweet, everything works, great, okay. Lastly, let's go ahead and do a visualization on that. Now, since we're interested in the relationship between whether or not somebody survived, what passenger class they were in, and as well as their title, we can only just use the labeled data, which corresponds to the train data frame, which, if you recall, was the first 891 observations. So we're going to call ggplot again, good old handy ggplot2, and we're going to say, look, use the data.combine data frame, but only grab the first 189 observations, the first 189 rows out of the table. Go ahead and grab all of the columns, all the variables, and I want an aesthetic where the x axis is the title, so that would be Miss, Master, Mrs., Mr., or other. I want you to color code it. I want you to fill it based on the value of the survived. Did they survive or perish? And then I also want you to then pivot that also based on passenger class. So in ggplot2 terms, that's called a facet wrap. And of course, as with everything, you can ask the help system about a facet wrap. And here you go. Facet wrap wraps a 1D ribbon of panels into 2D, which is not particularly intuitive description, so it's better just to see it. So once again, we'll go ahead and just run this and see what the plot looks like. And here you go. Now this is a very, very interesting plot, arguably. So here we have our facet wrap, right, for each P class, 1, 2, 3. So we've gone from 1D to 2D, essentially. That's what that not particularly helpful description from the help system was trying to imply. And down here we can see the titles: Master, Miss, Mr., Mrs., and other. And then, of course, they're color-coded. So right away, some things pop. First of all, if you are a Mr. in 3rd class, life is not so good for you. You were very, very likely to perish. If you were a Mrs. in 3rd class, you're about 50-50. If you're a Miss, about 50-50-ish. Master, unfortunately, you're more likely to die. Unfortunately, perish. So this is particularly interesting. You know, there's an old adage in the U.S. I'm assuming it's the same thing in the U.K. as well, maybe in Australia and other English-speaking countries, that women and children first. This kind of maybe bears this out a little bit, at least in 3rd class, because it seems like you had a better chance of survival in general if you were a woman or a child, as opposed to an adult male. Now, conversely, if you go to first class and take a look at it, things really pop as well. Again, this is even more striking, arguably, from this women and children first perspective, that if you were a male child, a female child, or unmarried woman, we can't make that assumption that a miss at this point is only a child, or a married woman, you are far more likely to survive than perish. But if you were an adult male, we'll use Mr. as a proxy for adult male, in first class, your odds were far less likely that you were going to survive. So this is more indicative of this idea of women and children first. This is also borne out very strikingly in second class as well, as you can tell by the relative colors. So this is a very, very striking plot from a data analysis perspective on this data set. And it's indicative of the power of doing data analysis and actually just looking at things and saying, look, is there hidden patterns? Are there hidden pieces of information within the data that could help me solve my problem at hand? In this particular case, embedded within the name string was this title thing that we were able to pull out and add as a new variable, or in machine learning parlance, add as a new feature to our data frame, to our table, to our data set, and then say, look, is this thing particularly interesting? And sure enough, it is. This title thing is extremely interesting, as you can be seen from this plot. Now, whether or not in the end, once we're totally done with our analysis, is it still as significant, or do we find something more? That's to be seen. But at this point, I think we'll wrap it up for this particular video. Hopefully, this is helpful for you, and it's piqued your interest in the power of data analysis and visualization using R, especially if you're interested in the data science of predictive modeling. Thanks for watching. Hope to see you again in our next video. Thanks a lot.